Hi everyone. Today's lecture is going to be about two problems that are pretty fundamental to working with historical data, which are OCR and record linkage. And so I'm going to start by talking about OCR, and then I'll record another video about record linkage. So digital texts are central to the study and the dissemination and the preservation of human knowledge. Tens of thousands of users consult digital archives daily in Europe alone, yet billions of documents remain trapped in hard copy in libraries and in archives around the world. And these documents contain extremely diverse character sets, languages, fonts or handwriting, printing technologies, and artifacts from scanning and aging. There's just an enormous diversity out there. Converting them into machine-readable data that can power indexing and search, that can power computational textual analyses with NLP, that can power statistical analyses, and that can be more easily consumed by the public, requires highly extensible, accurate, efficient tools for OCR. So OCR is typically modeled as a sequence-to-sequence problem with learned embeddings from a neural vision model, taken as inputs to a learned neural language model. And the seek-to-seek architecture falls short of the requirements that I just enumerated because it's challenging to extend and customize to novel lower resource settings. And that's because training a vision and language model requires a vast collection of labeled image text pairs and significant compute. As we've seen earlier in the class, right, seek-to-seek is incredibly data hungry. If you're training a seek-to-seek vision language model for OCR, you can't just start, with a pre-trained language model and expect that to perform well because it's taking vision representations as inputs. It's not taking tokenized text as inputs. So it really takes an enormous amount of compute to train a seek-to-seek vision language model, especially if that's a seek-to-seek transformer model. There's not commercial incentives to create the training data and the compute that would be required to extend that to low resource settings, and it's likely to be beyond the capacity of most academics. And so, for example, we find that on printed Japanese documents from the 1950s, the best performing existing OCR mispredicts over half of characters. This level of poor performance is widespread. It's generated a very large post-OCR error correction literature, which doesn't, fix all the problems in some sense because information is destroyed in the process of creating a noisy OCR. And more generally, the fact that OCR is not very extensible outside the high resource, settings that it's been created for its commercial purposes, the fact that it doesn't extend well outside those settings tends to skew digital history towards a limited number of settings that are not representative of documentary history. And so with Jake Carlson, who's a G1, and Tom Bryan, we developed an open source OCR called Efficient OCR, or EffOCR for short, which is designed for researchers and archives who are seeking a sample efficient, customizable, scalable OCR solution for working with diverse documents. And EffOCR is inspired by the simplicity of early OCR systems, starting in the 1920s, that focused on, as you can guess from the name, the optical recognition of characters, which is not actually what modern OCR does. And so EffOCR uses object detection methods to localize individual characters in a document image. And then character recognition is modeled as an image retrieval problem using a vision encoder contrastively trained on character crops. So let me talk in a bit more detail now about the EffOCR architecture and how it differs from the seek-to-seek architecture that predominates in that predominates in OCR applications. So modern OCR, regardless of the architecture, overwhelmingly uses a deep neural network, either a CNN or a VIT, to encode images. The representations created by passing an image through this neural encoder are then decoded to the associated text. And no matter kind of what your OCR architecture is, this is kind of the fundamental structure where you have an image and you need to encode that, and then you need to decode those representations into text. And so there are two key differences between EffOCR and seek-to-seek, whether that seek-to-seek is using a CNN or a transformer. So seek-to-seek architectures require line level inputs, and individual characters are not localized. Rather, images or their representations are divided into fixed size patches. And so despite being called optical character recognition, if you're using seek-to-seek, it's not actually localizing individual characters. In contrast, EffOCR localizes characters using modern object detection methods, like the ones that we saw last class, Cascade RCNN or YOLO. Okay, the second major difference between EffOCR and seek-to-seek is that seek-to-seek sequentially decodes the learned image representations into text using a learned language model that takes the learned image representations as inputs. And so you learn a model to encode your text line image, and then you decode that using a learned language model that takes the representations of that line as inputs. And this takes a lot of data. That's going to be a key thing. This is a complicated model to learn. You're learning to encode an image and then decode it with a language model into text. In contrast, EffOCR recognizes text by using contrastive training to learn a meaningful metric space for character level OCR. The vision encoder projects crops of the same character regardless of style nearby, whereas crops of different characters are projected further apart. And then character embeddings are decoded to text in parallel. So this is not require sequential decoding. Character embeddings are decoded to text in parallel by retrieving their nearest neighbor from an offline index of character image embeddings that is created from a digital font. And so in short, EffOCR, we recognize characters and then we create meaningful representations of those characters where characters, regardless of their font, their style, whatever background noise there is, etc., they're mapped nearby, whereas different characters, even if they look very similar, are mapped further apart. And then at inference time, when we need to OCR that, we just retrieve the nearest neighbor from an index of character image embeddings created from a digital font. And that's how we know the identity of that character. This contrasts to seek, where you're encoding an image of text, a text line image. You're not localizing characters. You're just taking the representations that come from that line of text and you're decoding that with a language model, which is a very data hungry problem, particularly if you're using transformers. Okay, so this is a visual representation of EffOCR as compared to seek. EffOCR localizes the characters and then it feeds them into the recognizer where we have this metric problem and representations of the same character are nearby. In particular, they're nearby that character in this embedding index that we use to decode that character into its text label. Where seek, we don't localize characters. We just feed them into an image encoder that gives us representations, and then those representations are fed into a language model, which is used to decode the text. And so this is an example of a CRNN, which is a common framework for OCR that uses a CNN and a recurrent neural network, specifically a bidirectional LSTM. So you see the input image is passed in, and that creates a feature sequence that is the input into the LSTM. Of course, because that feature sequence doesn't, the features of that don't correspond to characters because we never localize characters. In fact, when this framework was developed, the technology to localize characters, well, didn't really exist. We're going to get some duplicate predictions, and those need to be removed. In this case, that's done using something called a connectionist temporal classification loss. But as you can see here in short, if this was a transformer, it would look a bit different, but it's still the same basic idea. You encode an image, there's representations from those images. Those representations don't correspond to specific characters, and they're fed into a language model that then decodes the text that's in the image. You can see here specifically kind of the receptive field of the feature sequence in the CRNN, and you can see how those don't, necessarily correspond to characters. Okay, so coming back to EffOCR, different vision encoders can be used interchangeably for the character localizer and for the recognizer. And 3 models are considered: a vision transformer model, which we call EffOCR base. That's going to be an excite transformer, but in our supplementary materials, we also look at using a VIT and SWIN, and it doesn't matter, okay? It all looks very similar. We also have a convolutional base model, EffOCR base, and that's going to be a ConvNext, which is the state-of-the-art convolutional model, and a convolutional small model, which uses lightweight architectures designed for mobile phones. And so that's going to use YOLO v5 and MobileNet small v3. So in order to evaluate EffOCR requires benchmark datasets that are representative of the diversity of documentary history. And traditional OCR benchmarks focus on commercial applications like receipts. Receipts are not representative of the diversity of documentary history that we would like to be able to access for academic research. And so the study builds novel datasets. Our first context is historical Japan, and we draw on documents that can elucidate fundamental questions that have been understudied due to a lack of digital data, such as the drivers of Japan's rapid transformation from a poor agrarian economy to a wealthy industrialized nation. Horizontally and vertically written tabular data provide rich information on Japanese firms and their personnel. These come from 2 1950s publications, and a 1930s prose publication provides detailed biographies of tens of thousands of individuals. These texts could use over 13,000 kanji characters. The second context is Library of Congress's Chronicling America collection, which contains over 19 million historical newspaper page scans. Library of Congress does provide an OCR, but the quality is on average poor. So Chronicling America elucidates how EffOCR performs in the highest resource setting, which is English. It also elucidates its extensibility across Latin and kanji characters, which differ significantly in their aspect ratios and in their complexity. And finally, it elucidates the extensibility of EffOCR to many Unicode renderable languages that use the Latin script. And so this is example images from our benchmark data sets. And so you can see the historical newspapers, as well as, B is the horizontally written Japanese tables, C are vertically written Japanese tables, and D is the Japanese prose. So our benchmark data sets are fairly small. This is lines, which corresponds to like a cell in a table for the tables, or a line within an individual column or row for the prose. And so, 291 newspaper training lines is pretty small because newspapers have multiple columns. So there's not a huge number of words in a line. And as we'll see, this is actually quite a lot more data than we would need to achieve a high accuracy. Okay, but even then, this data was fairly straightforward to create. We're talking hundreds to thousands of lines or cells. Okay. And so in order to measure OCR accuracy, we use the character error rate, which is just the Levenshtein distance between the OCR string and the ground truth, normalized by the length of the ground truth. And so for instance, if you have a character error rate of 0.5, that translates to mispredicting approximately half of characters. Okay, And we're going to look at a variety of comparisons. So there's several leading OCR engines that we will use off the shelf. Google Cloud Vision, that's proprietary. You can only use it off the shelf. It can't be fine-tuned. We don't know what it's doing because it's proprietary, but it's very widely used. Baidu OCR, which is popular for Asian languages, also can only be used off the shelf and is proprietary. Tesseract, which is a bidirectional LSTM, we use Tesseract off the shelf because until very recently there were very minimal resources for fine-tuning it, and so most people didn't do that. And now they've added some more resources for fine-tuning, but that's recent and it's still pretty involved, and so we're just going to use Tesseract off the shelf, which is how the vast majority of people use it. We also have models that we fine-tune or train from scratch. So we use the convolutional recurrent neural network framework that I just showed you in the graph a few slides ago. That's implemented through EasyOCR's codebase. We use a transformer OCR, which is a sequence-to-sequence encoder-decoder transformer. There's base and small models that was produced by Microsoft, by researchers at Microsoft. And finally, we use Paddle OCR Single Vision Text Recognition, or SVTR framework, which also abandons seek-to-seek. It's also a vision-only model. It divides text into small, non-character patches using mixing blocks to perceive inter- and intra-character patterns and recognizes text by linear prediction. Pre-trained EasyOCR, Paddle OCR, and TROCR are fine-tuned on the same target data as EffOCR. Considerable resources have been devoted to pre-training these models. For example, TROCR was pre-trained on 684 million synthetic English text lines. It's a lot of text lines. And hence, these comparisons where we take the pre-existing models and we fine-tune them, elucidate performance when we're taking a model that's already been extensively optimized for OCR and we fine-tune it on our target data. Of course, that's not an apples to apples comparison because we didn't pre-train EffOCR on 684 million English synthetic text lines using some kind of massive compute cluster that only a large tech firm could afford. We want to do a more apples to apples comparison too, which is kind of the more informative, that's more informative about the architecture. We're just fine-tuning an existing model is the more practical question. You know, if I take an existing model and fine-tune it, how well does it do compared to EffOCR? Versus, you know, if we train everything from scratch on the same data, how does it do? That tells us about the architecture. And so we train from scratch on 8,000 synthetic text lines like EffOCR and on the same target crops. When I say train from scratch, I don't necessarily mean randomly initialize the model. I mean initialize it with whatever non-OCR tuned kind of checkpoint that architecture started with. You know, so for example, for TOCR, it started with a pre-trained vision transformer and I believe a pre-trained Roberta language model. Okay, so EasyOCR and Paddle OCR do not support vertical Japanese. TROCR does not support any Japanese, so obviously we can't do this on languages that the frameworks don't support. Okay, so this is the baseline results of EffOCR, and so you can see that for horizontal Japanese and vertical Japanese tables, the character error rate is well under 1%. It's a bit higher on the Japanese prose. That's because these are low resolution scans downloaded from the internet that are illegible in places, and we chose to include those because we want to provide a context where in theory language should be helpful. But still a fairly low character error rate. On Chronicling America, the character error rate is about 2%. And one striking thing here is that you can see the convolutional and transformer model look very, very similar. This small EffOCR model, which has less than 1/10 of the parameters of the base convolutional model, does a little bit worse, but the differences are pretty marginal, okay? And we're going to see that it gives you a huge speed up for kind of a very marginal decline in accuracy. So the ComNext model has 112.5 parameters. The MobileNet model has only 9.3 million parameters. And the baseline transformer model has about 102 million parameters. So there's really big differences in parameter count, and that's going to translate into even larger differences in inference speed when you try to get these things to run on a CPU. So you take a little bit of a hit with the models designed for mobile phones, but not much. Okay, now let's see how this compares. So first of all, when you compare it to the off-the-shelf stuff, you can see with horizontal Japanese, the next best alternative, Baidu OCR, makes about 10 times more errors. When you look at vertical Japanese, it's just everything's just horrible. It's going to turn out that the next best alternative is Baidu OCR, and that makes over 80 times more errors than EffOCR. So basically, like, the next best alternative for vertical Japanese is unusable, whereas EffOCR is extremely accurate. Chronically in America, Google Cloud Vision looks like it does amazing. Okay, we're going to see that there's a catch to this, and that this is not a practical solution. But when you feed Google Cloud Vision individual lines from Chronically in America, it does very well. And this speaks to the resource difference. That there's been a lot of effort that's gone into OCR in English, and considerably less effort that's gone into OCR in Japanese, even with this Baidu OCR that's supposed to be kind of the state-of-the-art for Asian languages. Okay, so this is off-the-shelf comparisons. When we look at open source OCRs that we can either fine-tune or train from scratch, so the next best alternative for horizontal Japanese is going to be Paddle OCR. Take the Paddle OCR model and fine tune it on our label crops, same ones EffOCR is trained on. It still makes about 5 times more errors than EffOCR. If you train it from scratch, it actually does considerably worse. This is kind of the next best alternative trained from scratch, probably because it's also vision only, but it still learns much less efficiently than EffOCR. Chronically in America, the other thing that's going to do reasonably well is TROCR base. This is a 334 million parameter model, so quite a lot larger than the EffOCR models. The other models do kind of significantly worse on Chronically in America than EffOCR. Okay, let's look at the errors that EffOCR makes. So here we have the ground truth crop, the EffOCR localized crop, and then the nearest neighbors, where the correct neighbor is shown in green. And so you can see here it's confusing a C for an E because the little line has largely disappeared. Here it's confusing an A for an N, and you can see why it does that. Here it's confusing an O for an E, kind of for the same reasons it confuses a C for an E, confusing an F for an R. Again, these are homoglyphs. You can see why it does that. This is a common error where it confuses an O for a 0 because it's just across different fonts, like an O in one font can be a 0 in another font. It's just a very difficult problem. Of course, this sort of common error is actually easy to fix in post-processing because you know a 0 doesn't belong in the middle of a word with text. And so actually a lot of these errors can be fixed in post-processing with a homoglyphic spell checker. And here it's confusing an N for a U. And again, you can see kind of why that's the case. In all these cases, it's the case that, either the character isn't really fully legible or otherwise it's a thing like a 0 and an O where it's just very difficult across fonts to recognize that always correctly. These are the Japanese errors. And you can see that there's 13,000 characters, right? And so there's a lot of characters that potentially look very, very similar to each other. And so you can see when it's making errors, they're very, very homoglyphic in nature, right? It's confusing characters that look extremely similar to each other. On some of these, I had to stop and stare for a little while. And again, sometimes with the low resolution of the scans, it's really not fully legible which of these it is. And so these are errors that are even kind of very difficult for a human to get correct. Okay. And so now let's talk about deployment. So you saw that GCV was the state of the art on individual lines from Chronically in America, but GCV makes significant layout errors when it's fed full newspaper page scans, which have complex layouts. And hence the performance you saw cannot even come close to being recognized when it's fed scans and not lines. And the problem is GCV charges per image, implying a cost at current prices of around 23 million US dollars to digitize chronically in America at the line image level, as compared to tens of thousands of dollars using EffOCR small. And so this is just completely cost prohibitive. And I've talked with some of you about this in other contexts where you were trying to use GCV and it seemed like what was going awry was line detection. But if you feed GCV individual lines, it quickly becomes cost prohibitive. The other alternative for the English was TROCR based, which did also somewhat better, albeit not hugely better. But EffOCR small is 31 times faster than TROCR base. That means that it's going to cost 31 times more to digitize chronically in America with TROCR base, which is likely to be cost prohibitive as well. And so EffOCR supports inference parallelization across characters, whereas with the seek-to-seek, you have to do autoregressive decoding. And so that plays into, why TROCR is so much slower and suggests that this is kind of a more reasonable way to use a transformer for OCR. On English, the most plausible, scalable alternative is fine-tuned easy OCR, so that's a much smaller model. So even though it's seek-to-seek, it's actually faster because it's much smaller. But the character error rate is higher. And another thing we don't get into here, but this evaluation data set is just 10 randomly selected newspapers. And as Tom will tell you, if you look at the whole kind of nearly 20 million scan collection, there's a much longer tail of weird stuff. And because EffOCR has very good few shot performance, we can add a few labels from that weird stuff and do well. Whereas these other less sample efficient architectures take longer to learn that weird stuff. And so I think, on the full chronically in America, the advantages of EffOCR are plausibly larger even than what's shown here. For horizontal Japanese, EffOCR small is nearly 5 times more accurate and faster than paddle OCR fine-tuned, which is the next best alternative. Okay, so this is the inference speed table, and kind of, you see what I was talking about. Easy OCR is the fastest, it's also smaller, but after that, EffOCR small is the next best, and it's going to be much, much faster than the base EffOCR models, because these models are over an order of magnitude larger in terms of the number of parameters. And so while it's, a little bit less accurate, it just, the trade-off in terms of faster speed is pretty substantial if you're trying to digitize things at scale. All right, so sample efficiency. EffOCR has a very parsimonious vision-only architecture that allows it to learn efficiently. And to quantify this, we take EffOCR base and compare it to leading open source architectures pre-trained from scratch on the same number of synthetic text lines as EffOCR and tuned on the same target corpus. So EffOCR learns faster than both seek-to-seek alternatives, so CRNN and TROCR, and competing vision-only SVTR architectures, with the next best alternative making 16 times more errors for Japanese and 4.7 times more errors for chronically in America. The transformer seek-to-seek model in particular is unusable. You can see that here. From scratch, it's getting kind of most characters wrong, and that's just because it's extremely data hungry to learn a seek-to-seek transformer model, and it doesn't really help you that much, right, to start with a pre-trained Roberta or whatever, because it's not taking tokenized text as inputs, it's taking images as inputs. All right. Strikingly, on as few as 99 labeled table cells for Japanese and 20 rows for Library of Congress chronically in America, which is a 5% train split, the character error rate of EffOCR is only 5% for Japanese and 7% for English. So this shows very viable few shot performance. You can label 21 rows from a newspaper column in a matter of minutes. and it's already doing pretty well. And so this is just showing you on Chronicling America and on the Japanese with different trained test splits. So 0% would be just on synthetic data. You can see already at a small number of labeled crops, it gets, EffOCR gets quite accurate compared to the others. And then at 20% trained split, it's almost as good as at 70. And then kind of everywhere, it's kind of doing better, or at best, kind of at worst, similar to the other architectures. And so this is just showing you the EffOCR. It's really able to learn, more efficiently. And in particular, it's learning way more efficiently than a seek-to-seek transformer model, which you can tell is like, as I said, tier OCR is trained on like 670 million or something like that synthetic text lines. So in the realm of like, R tuning on, dozens. It's just not like dozens to a few hundred. It's not really learning much at all. Okay. We also look at some ablations. So you can use, instead of using contrastively trained character recognizer, you can use a feed-forward neural network, and it's a little bit worse, but not that much worse. We go with the contrastively trained model because it is slightly better, and because using FAISS as the backend makes it really fast. You turn off hard negatives, and things definitely do worse. Okay, when we talked about contrastive learning, we talked about how hard negatives are important, and this is no exception. Let's say you forget about pre-training on synthetic data and just use our, hundreds of labeled crops to train on. That does really bad for Japanese, which is not surprising because there's 13,000 characters and not all of them are even in our labeled data. And so the model would have literally never seen some of the characters in the test set. On English, it's actually not that much worse to just train on a few hundred characters because there's not that many characters in English in the Latin script, and they're all covered in the training data. The opposite is actually true for the localizer. And so kanji characters are basically all squares in their aspect ratio. So learning that to localize characters is like a trivial problem, whereas learning to localize characters in English is harder because they can have very different aspect ratios. And then finally, we can use different encoders. So SWEN or VIT base, and sometimes it's a little worse, sometimes it's a little better, but basically kind of they're all pretty similar. It doesn't make a huge difference what encoder you use. Different encoders that are well trained learn similarly good representations. Okay. So EffOCR can convert the publications examined in the study into a knowledge graph that provides rich information about network relationships in the historical Japanese economy. And these relationships can be observed through shareholding patterns, family ownership, financing, board of directorship networks, occupational histories, family connections, spatial locations, and supply chains. These can all be constructed with those publications. So just an incredibly rich and granular understanding of networks in the Japanese economy, and that can all be combined with rich financial, production, and biographical information. Japanese individual and firm names are often only a few characters long, and hence a single OCR can create a significant information bottleneck in creating these networks. And that was really our motivation, to think about custom OCR in the first place, is that I wanted to OCR these Japanese books, and it really took a very, very accurate OCR to build networks. You can't just sample them and digitize it by hand, because we know that sampling a network, even if it's random, will lead to kind of biases and statistical analyses. And so kind of being able to digitize these books was the motivation for going down this road in the first place. So the paper provides an illustrative example of one component of the graph showing supply chain networks in 1956 that were constructed by using EffOCR to digitize the customers and suppliers of Japan's 7,000 largest firms. Fine-grained control through EffOCR allowed us to detect an atypical character separating firms in the customer-supplier lists that other OCR solutions did not systematically recognize. And this one character was actually super important, because if we don't kind of separate the firms in these lists, which are just separated kind of by this atypical character, then like the whole thing will get screwed up. And so this again shows kind of the power of a very sample efficient customizable OCR. You might have one character that's super, super, super important that you get it right. And it's very easy to tune EffOCR to do that. Each node in the graph is a firm whose size is proportional to its degree centrality in the supply chain network. And shading denotes the big three firms in pre-war Japan, Mitsui, Mitsubishi, and Sumitomo, as well as other firms comprising Japan's largest conglomerates that were targeted by the Holding Company Liquidation Commission in the late 1940s that tried to break up large Japanese firms. So these are the supply chain networks in 1956. And what you see from this picture is that kind of the big three pre-war firms, as well as the other HCLC targeted large firms, tend to be the most central firms in Japanese supply chain networks after the war, despite significant efforts to break them up in the late 1940s. And so the many different types of relationships between individuals and firms that can be accurately captured by EffOCR can facilitate a much more granular, comprehensive study of Japan's economic development than we could achieve with the aggregate data. And again, this was kind of really central to the motivation to go down this route, and I think really nicely showcases the things you could do with EffOCR that would just be impossible to study without it. All right, and so now I want to give like a little bit more commentary on what are the important features of EffOCR and why did we choose them. And so if we hope to index and analyze and disseminate and preserve a diverse documentary history, we really need a community engagement of stakeholders like you all with the requisite fine-grained knowledge of the relevant settings. You know, I'm not going to go and be the one to digitize historical documents from Germany because I don't know that context. I don't have that knowledge. We really need academics who have knowledge of historical Germany to be engaged in digitizing and disseminating, preserving, studying those documents. And EffOCR facilitates this engagement because it is highly extensible to low resource settings, it's sample efficient to customize, and it's simple and cheap to train and deploy. In contrast, Seek-to-Seek is more aligned with the commercial objective of designing a product that is difficult for your competitors to imitate. So EffOCR can be trained in the cloud with free student compute credits. And it's very straightforward to do so, whereas TROCR required training on a multi-million-dollar cluster that had 32 gigabyte V100 cards, which basically only like a tech firm like Microsoft could afford. I don't know of any academic who could really afford that type of cluster. Besides that, lower resource languages lack the pre-trained large language models required to initialize a transformer seek-to-seek model like TROCR, so you can't even initialize it. And compute resources and data for training are also likely unavailable. So EffOCR encourages community engagement by combining this parsimonious conceptualization of optimal character recognition, OCR, not word recognition with a language model, etc., from nearly a century ago with the AI revolution, and it integrates the following features. It's character level, it has language extensibility, it decouples localization and recognition, it's open source, and it's scalable. So let me say a few words about each of these features. EffOCR creates semantically rich embeddings of individual characters, and this is a very parsimonious problem. Just like children learn the letters of the alphabet before they learn to read, it's easier for an OCR system to learn that this is an A and this is a C and this is a D than to learn how characters are used together in complex ways to form languages. So annotators can select which of the most probable character predictions from the pre-trained recognizer are correct, potentially using a simple mobile interface. And so this is also great for efficiency of labeling. Or if you have line level labels, they could be mapped to the character level once a localizer has been developed. Language modeling advances have concentrated around less than 24 modern languages, and so there's just been such a huge emphasis lately on large language models, but we shouldn't forget these are like, they've only been developed for the highest resource languages, and there's thousands of languages out there. Language differed historically from language today. And by the way, if you're digitizing tables, you don't need a language model anyways. And so omitting the language model makes EffOCR extensible and easy to train. To extend it to a new language, all you need are renders for the appropriate character set. Additionally, characters do not need to be seen in sequence during training, so new characters can be added at inference time. And this is really valuable for contexts where new characters are regularly discovered, like archaeology is the most obvious context, but maybe you're just digitizing historical documents and you realize at inference time that there's some weird character in there that you need that you didn't train the model with. Well, you can just add it at inference time, and that's fine because it doesn't need to be seen in sequence during training to be recognized. Omitting the language model makes it easy to mix and match scripts, which is necessary for some languages, particularly some endangered languages. The recognizer can also be exposed to characters in training using any desired sequencing. This is not true of multilingual seek-to-seek training, and so we know, like for example, the GCV trains at the script level. So as multilingual training at the script level, there's been work done showing that this leads to many OCR errors with endangered languages because they use characters, maybe they use the Latin script, but they use characters that are very rarely used in English, which is the majority of the training data for the Latin scripts. Whereas, it doesn't matter what kind of weird kind of distribution of characters your document uses, you can modify training to take account to that. It gives you very fine-grained control over that. Okay, decoupling localization and recognition. So in EffOCR, we separately train the localizer and the recognizer. Theoretically, localization and recognition, which is akin to classification, rely on different features of the image, and that suggests modularity. Practically, decoupling allows localization and recognition to use different training sets, and that economizes on annotation costs since these tasks can require a very different number of labels depending on the script. We found this is very important. So for English, you don't need many character labels for recognition because there's not that many characters, but aspect ratios are weird, so you may need more character bounding box labels for the localization, whereas the opposite is true for Japanese. You don't need many bounding box labels to localize the characters, but you might need more labels for recognition, and since creating these labels is very costly, it really helps to be able to decouple those problems. This also encourages community innovation and future-proofness because it significantly simplifies training to decouple localization and recognition and makes it very straightforward to swap encoders as the literature advances. So if there's something that's way better than convnext, you just plug it in and it's very straightforward to do that. EffOCR will be integrated into Layout Parser, open source package for document image analysis, and finally EffOCR Small achieves fast CPU inference that can cheaply scale to hundreds of millions of documents. Okay, limitations and future directions. First limitation, EffOCR is not currently an off-the-shelf solution, rather it's designed for contexts where you need and you want fine-grained control. The sample efficiency of EffOCR does suggest the feasibility of designing an EffOCR that works well for many applications off the shelf by exposing the pre-trained model to a modest number of crowdsourced crops from a wide range of documents. And so this is something we may try to do in the future. Another next step is to build upon the data augmentation and style transfer literatures to generate more diverse synthetic pre-training data. We didn't put a lot of effort into synthetic pre-training data, but I think we could generate more diverse and realistic synthetic pre-training data with more sophisticated methods, and that would also make it work better off the shelf. We don't focus on handwriting. That's due to space constraints. The approach would be analogous. Synthetic handwriting generators could provide extensive data for pre-training, analogous to the study's use of digital fonts, and I think as long as the handwriting is legible, this will work well. If large portions of a document are illegible, either because it's horribly illegible handwriting or because there's been noise from printing and scanning and aging, etc., language can provide educated guesses. So if lots of your document is not legible, I can tell you from experience you're going to have a hard time, but maybe kind of you want to try to use something with language and see how that does, because there's just no way you can get at it without making educated guesses through language. Moreover, the heavy use of literatures and some character sets and handwriting could lead to more challenging character localization, At the same time, modern object detection methods are incredibly powerful, and synthetic pre-training can encourage robustness to localization noise. And so I think, and we've seen in what we've done, that there can be kind of a fair amount of localization noise, and as long as you train the recognizer to be robust to that, which you can do with synthetic data, it kind of can work surprisingly well. Okay. So there is an emerging literature that explores foregoing OCR altogether to just directly reason on images. The main focus of this literature is commercial applications like receipts and train tickets. And there are not end-to-end models for performing research tasks, like running a regression with the data in the table. You're digitizing. Obviously, you're not going to be able to run a regression, do statistical analysis on your image, right? OCR is likely to remain relevant for academics and digital archives for the foreseeable future. And EffOCR's simple character image retrieval framework can hopefully expand accessibility to a rich diversity of human knowledge, making it easier for all of you to do research outside of high resource settings, do research that's kind of an aggregate, kind of more representative of the diversity of documentary history. All right, so I'm going to make a second video on record linkage, so please also go and watch that video before class on Tuesday, and I'll really look forward to talking to everybody more about OCR then. Thank you.